Hi, this video we will be talking about mass flow rate. So mass flow rate, abbreviation MFR, and often we use m dot. Whenever I have a dot, that means it's divided with respect to time, the first derivative with respect to time. So mass flow rate, the definition is how much mass of this fluid is passing through over time. So knowing that the US unit for mass flow rate, that will be how many pound mass per second. And for SI unit, metric system will be how much kilogram of mass passing through every second. So the second point we'll be talking about is how mass flow rate related to volume flow rate. V dot means volume flow rate. Same concept. If it's dot, that means derivative by time. So before we make the connection, we have to see what's volume flow rate. Volume flow rate is how much volume passing through per second. So for US, that will be how much cubic feet per second. And for SI unit, that will be how much meter cube per second. Now, we are trying to relate mass flow rate with volume flow rate. It's times what value is, right? So here we're going to use dimension homogeneity to help us figure out this missing puzzle. Dimension homogeneity. What that mean? What does this mean? That means left-hand equation and right-hand equation, they have to share the same dimension, same units. Okay, so example, if this is in kilogram and this have to be a mass unit, can be a pound mass or kilogram or anything. You cannot relate kilogram with time, can we? No, right? So that's dimension homogeneity. And this actually concept is quite often used for engineering. So for example, for this problem, mass flow rate we're already talking about in SI system, that will be kilogram per second. And volume flow rate in SI system is meter cube per second. Then what will be this missing link, right? Okay, so let's just have to play with it. They both have seconds. However, this have meter cube, so we're gonna put meter cube at the bottom so it can be canceled out. And we want to get kilogram on the top. So looks like we have a solution for this now. What is kilogram, which is mass, divided by meter cube, which is volume? What is mass over volume? All right, mass over volume is going to be our density rho, right? So now you got the missing piece. So here we can write down this entire equation. Mass flow rate is going to be equal to volume flow rate times density. And this is extremely helpful. Okay. So knowing that, we are going to review another quick concept about volume flow rate. So volume flow rate we're talking about, it's volume over time. And volume flow rate is related to velocity. It's velocity times something. Okay, we're going to use dimension homogeneity again, trying to figure out this missing puzzle right here. So volume flow rate in SI unit is going to be how much volume passing through meter cube per second. And the velocity is distance traveled per time. That's going to give us meter per second, right? Meter per second, that's velocity. Then what would be this missing link? They both have seconds, and so this one will be equal to meter square. So what will be meter square? That's going to be our area. So knowing this, we have another equation for volume flow rate. Volume flow rate is velocity times our cross-section area. Those are two important equations. So now we are going to go back. So quick summary. Mass flow rate is volume flow rate times density. However, in thermodynamics, we don't normally use the density. We use specific volume, which is small v. Specific volume is reciprocal of density. So knowing that, we can continue to write down this mass flow rate equation. That's going to be volume flow rate. Rho, here density is going to be reciprocal of specific volume, so times 1 over v. In other words, it's volume flow rate divided by specific volume. That's going to be our mass flow rate. So we have another expression for mass flow rate. It's going to be volume flow rate divided by specific volume. And this equation actually was quite used in thermodynamics. And also we discussed about volume flow rate right here is equal to velocity. Here, be aware this small v is velocity, not the specific volume. So I spell it out. It's velocity times cross-section area. Okay, so those are the two important equation to be used for mass flow rate and a volume flow rate. So in the next video, we will be looking at some examples using this mass flow rate and volume flow rate. See you next time. Bye now.